Alrighty. So let me pull up the different thingamadoodles. Okay. So with regards, oopsie, yep. So yep. So PA5 then says it's essentially an assignment over graphs, right? And the specifically what we want you to do is not only design the graph data structure, but also perform a specific sorting algorithm on it, topological sorting. And then, of course, there's a report. Now, we'll deal with the report here in a second. But down the zip folder, I know that per a campus wire post, there's some issue with it. There's some issue with some of the data files. I have not been told yet what those issues are, so I can't fix them. So as soon as I know what those issues are, I think it's in one of the data files or something. Maybe, because I remember something similar happening last semester, but I forget if we fixed that or if it was actually on purpose. Anyway, but yeah, so that's there. Homework 3 then, generic overview is essentially it's over things we have already covered as well as things we're going to cover. So think your hash tables, your heaps, priority queues, and spanning trees and graph algorithms. Okay, so as with most of the other homeworks, you'll have to do some sort of runtime in it. There's also an overleaf template here. And what's it called? Yeah. So it's duplicated in a couple of different places. So these are all should be ultimately the same. And then yeah, let's deal with this here. Okay, good. So yeah, so again, PA3 is going to be due on, or PA5 is going to be due on the 26th, which is just 11 days from now if you count today. Then homework 3 is due 27th, which is 12 days from today. Okay. Now, let's see here. So we go, yeah. Wait 1 second. Okay. So if you open up that PA5 file, the PA5 zipped folder, there'll be quite a few. There's quite a few things in there this time around. Most of it is redundant. You don't really have to worry about too much about it. There are some optional tests or some optional data files that you can use if you so choose. So that's kind of up to you. Oh, geez. It's lagging. It's okay. Anyway, so the idea that means we have a couple of different things in here. So mainly we have two different bits of code. So we have graph.h and then main.cpp. Okay. And we also have a decent few data files, right? Which are probably going to be used for something. If I could go. Okay, fine. Yeah, I should be able to open up. Really? I guess it's just because it's in this. Yeah, this is just different. Yeah. So namely, so you have the PDF. So the main things to note, you have PDF, you have the 2 bits of code, and then you have some data files. Okay. So if we go over here, so the main file you'll be the only file you'll be really messing with is graph.h. The main file provided does something pretty simple. It just tries to create an input stream with some file input, and then it then tries to build the graph based on that input, and then displays the graph, computes the in degree of the graph, which is something hopefully I've learned about. If not, it's okay. And then tries to perform topological sort on the graph. If it succeeds, then the ordering is printed at the screen. Otherwise, there must be some cycle in the graph. So then you can sort of split this up in your head into 3 different parts. It's not split into 3 different parts, of course, over on Mimir, but if it helps to think about that, you can think of it like that. So you have your general data structure that you need to implement, that being the graph. Next thing would be doing a topological ordering for a directed graph. And then lastly, be the report discussing part 1 and part 2. Okay. So if you look here, so in part 1, it's implemented a graph data structure based on an additional data type we've already defined for you called vertex. It says this thing right here. So per in class, right? So you should have already hopefully learned about vertices and edges, right? So vertex can be thought of as just the nodes that are connected by different edges. Okay, so that's what this thing represents at the end of the day. Just represents one of these nodes. Okay, so within these nodes, you have a couple of different things. You have a label, which can just be thought of as the like the number or like the character or something that represents what this node is. Okay, then you have an adjacent ADJ underscore list, which is just this node's adjacency list, so telling you where these edges are, right? So telling you that, hey, B goes to this node and B also goes to this other node, right? Something like that. Okay, and then you then have an in degree number and a top num number, so you can that'll be explained here in a second. But this is a basic idea of what this represents. Okay. So we pop back here. So there's a couple of different functions you'll need to do. So namely, you'll need to do build graph, which is just constructing the graph based on the input file. So the input file itself is right here. Okay. So the way to read this is you have the first number, which is the label of the vertex you're dealing with. And then every number after that is the adjacency list for that first node, for that first vertex. So it makes it pretty easy to figure out how you might want to go. Okay. Also note these are in order. That's just because. And if something, it's also possible for nodes to have no adjacency lists. So keep that in mind. So you also, of course, need to just be able to display the graph in a very similar manner to this to output it. And then you should be able to figure out where a given vertex is based on its label. So you have inside of the graph.h, right inside of here, one idea we had is, okay, so like you might want to use something like a hash table, which in C++'s terms is an unordered map. This simply takes in, so to mean you feed node set a type T and it gives you out a vertex of type T. So this will map your label of the vertex to the vertex itself. Okay. So it's obviously, it's a little bit easier to deal with than say a vector of vertices, because this you can get faster access times as opposed to having to search through the entire vector to figure out where the thing is. Yeah, and then also note once again you have an assignment where there's no pointers. So therefore, you don't need things like the constructor or destructor necessarily, unless you want to use something other than a hash table, or you want to mess with something like that. Okay.
Basically, if you have pointers inside of your graph data structure for some reason, you'll need a destructor.
Yeah. So then last function being the size, so it just returns the number of vertices in the graph. So node set has a built-in .size function, or the unordered map has a built-in .size function. So yeah, pretty sure it does. If not, then shouldn't be hard to figure out. Yeah, so you encourage to use a hash table, as it says. Unordered map is one such data structure. Yeah, so being you build the graph using data, as I already said, or reading a data from text file, and then yeah. So the example I showed earlier results in this graph. So 1, 2, 4, 5 results in vertex 1 being created with links to 2, 4, and 5, right? And then the next one, 2, connected to 3, 4, 7. So 3, 4, 7. 3 is connected to 4. 4 is connected to 6 and 7. 5 is connected to nothing. 6, 5, 7, 6. Okay. So we assume then that we're dealing with a sparse unweighted graph. So notice that there's no numbers, right? There's no like path. There's no like cost to travel along any of the paths. So therefore, we're going to use adjacency lists instead of the adjacency matrix that was discussed in class. And the so nodes are not numbered consecutively necessarily. So therefore, hash table would be best for dealing with things. So you can assume So after building the graph, so you don't have to figure out how to insert or remove from the graph. You just have to figure out how to build it and then perform operations on it. So you don't have to deal with that. So then it says the display graph should print out the vertex and adjacency list on the screen. So as you can see, the output is fairly similar to the original input file. Okay, the only difference being in between the vertex and the adjacency list, there's a colon right here. Okay, that's about the only change because we're not inventive. A further note: so whenever you do the unordered map, whenever you print it out, it'll end up the value for each vertex key is going to be its label. So the label, so in this case, 1, 2, 3, 4, 5, 6, 7, that would be your key, your general type T. And then those would all map then to vertices on the per the hash table that's defined right here. So the idea being the label of a vertex maps to the vertex object itself. So that allows you to more easily figure out what vertex you're talking about because you can keep track of which vertex you're at. Does that make sense? So the vertices label maps to the vertex object itself. So that's how you can sort of store things. So the other thing, so because you have an unordered map, when you output things, it won't necessarily be in the order that you put them in because as it says, it's an unordered map. That implies that your stuff is going to be unordered. Hint, hint. But Mimir doesn't really care about that. So it'll, as long as all the things are correct in terms of what it's printing out, then it will accept it as being correct. So you don't have to worry about that. So I already have a makefile defined for you. I guess I'm pretty sure. Let me go pop it up real quick. Yeah. So this main file then. So one thing I'll mention now. So remember we said we split up into part 1, part 2. So I believe it's noted later. Maybe not. I don't know. So you don't have to understand what this is doing. This is the exact same thing as your normal makefile. It's just using fancy things like variables. which you can do because this is just makefile is just a fancy script. So scripts, you can do variables with this $sign. So that's what these are. Okay. So just know that main rep maps to this, obj rep maps to this. Okay. And then CXX is just compiler flags. So that CXX maps to this entire thing. Okay. So one thing to note, so this makefile as it stands will only work for part 1. Whenever you start to do part 2, you will need to comment out. I can do that. I can't do that because it's a read only file. It's okay. So you would comment this out with a £, hashtag. Then you'd uncomment this part out, and this becomes your your new one for part 2. Because you'll need to make another. Because you'll need to make another file, and then you'll end up using this other file to create the ultimate thing. To create your final product. Okay. So key thing to note there, you will need to actually go into your makefile and modify some things to make it work for the different parts. That's on purpose because now you can focus on the graph data structure itself before you worry about topological sort. Okay. Now, topological sort itself, so maybe ask yourself, what the heck is it? Well, formally, it's the idea that you have a directed graph with n vertices without cycles. And topological ordering can be thought of as an ordering such that for every edge in the graph, I is less than j. So what's that mean? Well, what that means is that in your adjacency list, you'll have a certain order that things will go in, and you just kind of follow that order. So in vertex 1, the number 2 is the first thing in its adjacency list. So in the final sorted order, then 2 should appear first, and then some later point 4, and then some later point 5, because that's the way it is in one's adjacency list.
Is
that the way I think about it, or no?
I don't think that. You add something to the vector at the end when its integrity becomes 0.
Yeah.
Yeah. Like it'll
Right.
look at 2 first, but it doesn't mean that it'll be before 4 or before 5 by necessity.
Yeah.
And this one, it happens to be that way, but.
Right. Yeah. My bad.
You're good.
Yeah. So for topological sort to work, you have to have a graph first of all. So you have to have called build graph to make your graph, and then you can call topological sort. So we'll use the algorithm from the textbook, which is copied below down here. And we would want you to do, or what you can do, there's a couple different ways to do it. So at the end of the day, what you'll get, is you'll essentially get a correct order of your vertices. There's a couple of different ways to store that. One way is to use that top num variable from earlier, which can allow you to keep the order of vertices in that way. You could also take the you could also store it in some external data structure as well. So you could take, say, a vector or something and store the vertices in order per topological sort in that. But the main thing being you have to print out topological sorting by printing labels of vertices. Okay. So in the end, then for part 2, you have 3 different functions. You have topological sort, which of course does the actual sorting. You have compute in degree, which figures out the in degree for a given node for all the nodes, which is important in the algorithm down here because that's how it works. And then you have print top sort, where you print the whole thing. And of keynote, right? So you have this Boolean here, Boolean variable, which tells you whether or not to add a new line at the end. So otherwise, if that is false, you do not add a new line at all. So you just print it out. Well, actually, yeah, I guess, yeah. So per the graph up here that we've been using, this is the topological sorting order, which I will explain in a little bit. So yeah, so this might require something like a priority queue, which would alter the runtime. So if you think about it, right, like optimally, these things do have a certain theoretical runtime, but for implementation purposes, like if you use something like a priority queue, that would obviously make the runtime not linear. That'd make it n log n because you'd have to build the priority queue and all that.
So I mean that your priority queue was a heap.
Yeah. So then for testing purposes, then you can use the optional ones if you want. So then the last part is just the graph data, or sorry, no, the report. So as with PA3, we just have a series of questions that we want you to answer. So namely, so describe your implementation. So think of that as how did you do what you do, right? So the description of functions, things like that. And then C++ features use assumptions to input data. So in regards to C++ features, that would be something like templating, inheritance, things like that. Assumptions on input data being like, okay, given like something like this file, what are you assuming about this file in order for your graph to work? In order for you to be able to build the graph, right? And then you then need to, so the algorithm down here uses a queue. So even if you don't end up using this pseudocode to figure out topological sorting, still we want you to figure out why, or at least explain why this algorithm below uses a queue, and then explain, and then state whether or not we could use a stack instead of a queue, right? And then explain how the algorithm down there detects cycles. So one of the issues with topological sort is that if your graph has a cycle in it, you'll get an incorrect sorting because the algorithm will essentially get stuck in or in the cycle, and then it will exit out without having visited all the nodes. So that's a problem. So the algorithm that's below has a very smart, easy way of figuring out whether or not there's a cycle. So you need to explain why the text cycles, not how the text cycles. So that's the key distinction there. It's like, why do we need why do we need the text cycles in the first place? Which I remember now I've just said. It's okay. So then running time for each function, same thing we've been doing before. Shouldn't be too hard. So then in regards to this testing requirement, so it's just screenshots pretty much. So you'll just run your code against these different cases, and then you'll get some output, and we want you to give us that output in form of a screenshot. So you might have noticed there are a couple of different input files in here. So we want you to run input.data, which is this sort of abstract numbering. We then want you to output input2.data, which is going to be a CSCE course list, which I'm told is might not be correct. So I'm going to maybe fix that later. But the idea being this is going to be a bunch of strings. So instead of having it just be integers, these are all just going to be, well, actually, I don't think they're strings. I forget if they are or not. Yes, because I think there are two different variants. Yeah, there's two different variants to this one, and I'm pretty sure one of them is correct and the other one's not, from what I recall, unless you fixed it. Yeah, I see where the issue is. Yeah, there's no. Okay, I'll fix it later. In here 313 is missing, and in here it's not. So like, yeah, because basically in here, 6 needs to exist, and then 2 needs to be connected to 6. I'm pretty sure. Yeah. So the way to read this is that like a like if a given class is a prerequisite of another class, then it's connected to it. So 121 is connected to 221 because it's prerequisite. Okay. So and then following that idea. So then 222 is also 221's prerequisite. 222 can also be, there's also a prereq for 411, things like that. So that's how that is supposed to be read. I'll get this fixed later. So then we then have another sort of variant on that being language arts courses. So that would be this input, or this one we want you to make by yourself. So we don't actually give you an input file for this. We just tell you, okay, similar to the CS courses, here are the course listings and here's the prereqs for each course. Build a data file with this information in a similar way to how this is done. So as I said, so your prerequisites point to your course. So 121 has a link or has an arrow, has an edge pointing to 221. 221 does not have an edge pointing to 121. Okay, so keep that in mind. Okay, so then the very last case is a case specifically designed to test your cycles, see if you can detect it correctly. So there's one of them called that. Then at the very bottom, we have basically a long set of explanations, or I guess not explanations, but sort of helping y'all figure out how the heck all these things work. Trying to anyway. Yeah. Right. So first of all, you have the pseudocode here for topological sort, which is this. So again, once again, it's a pseudocode. This one's a little better than our previous one. But the thing to keep in mind with this is that so there's certain things about this that you'll have to mess with in order to get this to work. As it stands, at least as I recall, there are certain aspects that you can forget about and mess up. So yeah, just as a heads up. So then, right. So then in terms of it, it says at the end here, you can see there's this little if statement, right, which figures out whether or not essentially you have a cycle. So that would be the how of how the algorithm figures it out, but you need to be able to tell us the why in the report. So for calculated in degrees, this would be the compute in degree function in here. So again, we have these 3 functions declared, but the idea being these will be defined in topological sort.cpp if I'm not mistaken, or they'll just be defined here.
Graph.h.
Okay.
I think they're just declared here.
Yeah. Again, I'm not sure because it said on the thing. Yeah.
Let me verify that.
Yeah, you very clearly tell that this has gone through multiple iterations and certain parts haven't been taken out.
Yeah, it's in the graph.h.
Yes, I'm pretty sure it's only in graph.h.
There's only 2 code files. There's graph.h
Yeah.
and main.cpp.
Okay, yeah. So scrap the bit I said about having a separate file. You just have graph.h. So yeah, so you have these different things here. So the topological sort code then can be thought of as this guy up here. Then the compute in degree function is these 2 loops right here. Now, the one thing that I'll note with these that you should be able to do, so this should be able to be done with only 2 loops of depth. So you shouldn't have to do 3 loops. you should be able to do this in 2 loops, or 2 loops deep. So the first, like this part of it, or this initial part of it, would be a single loop, right? And then this part of it down here, which should be 2 loops, because you shouldn't really, or rather, because you can go access things in the hash table and manually mess with their in degree. Yeah. So as we say here, so there's a couple of different containers you can use for this that store nodes in or store things in a way that is easy to reference. So the unordered map is like the easiest one to use and explain, but there's also things like, just the map data structure, as well as set and unordered set. So the code down here is basically explaining how, or like sort of going through these different things that are used. Yeah. So things like iterators, working with STL data structures, so there's some handy things that you can maybe deal with. You don't have to know this to do your topological sorting or anything like that. It's just helpful information if you want it. Down here, then say as another thing you might be using for the first time is priority queue implemented via binary heap. So the way this works is you have a, the priority queue needs a specific class to act as its, the way it compares things within the priority queue. So the way you declare it then is you give it the type that it's going to have. You then give it some data structure to hold it in. So say a vector, vertices, and then you then give it some comparator, which will tell it how to sort of, or how to go about sorting it. Okay. So up here at the top, commented out is that comparator function that you can use. You don't have to use it. There are different ways to get your topological sorting output, but this is the most helpful way if you want to deal with it. Okay, so again, there's a lot of different ways to go about printing that topological sorting order. Priority queue is one way. There are a couple of different main ways that I've seen. But yeah. So then, other than that, that's pretty much it for the PA. Now, one thing I will mention real quick, sent out via an announcement. So as we say here, so this is an optional thing for this PA that we're experimenting with, because as we are moving back to in-person here next semester, we wanted to test out this idea of essentially doing the report, but doing it in the sense of you answering questions instead of writing some stuff. Okay, so the idea being, so in order to, so as it says, in order to reduce your workload, provide real-time feedback, you can complete the PA5 report by telling us, right? So if you don't want to do it, then you just do the standard report as you've already done in previous assignments. So yeah, it says here, so we just want you to understand how your code works, and then you should be able to answer the questions in the report with justification, and you should be able to also run the code on your own computer. Specifically, you should be able to run all the files that we said and get the correct output. Okay. So then, so the report's due on the 26th. So when the date, or the tentative date we would have is that you'd hopefully be able to tell us or give that oral report next lab period or during our office hours, depending. So you can visit any other TA's office hours to do this, not just your lab TA. So it's sort of on you to make sure you do that. That's not on us, because like you still have the written report you can do. So if you want to do this, you'll have to figure out a time that works best for you to do this. Okay. That being said, as he recommends, make sure you're ready at least a day before the deadline, because many students join office hours the day the assignments are due.
Yep.
So just a heads up. So you should be able to share your screen, talk with us, and run the program with the examples. Before you're like, hopefully before you give the final report, you should upload your final version of the code to Mimir. So in other words, you should be able to get a perfect score or whatever you're wanting to get before you give the report, because we'll calculate your score right then and there and then upload it to Canvas. So you only have one chance to present, so make sure the output's correct. So it's not anything different than the normal report. It's just that we're trying to give it in a more, I guess, informal manner to, because of course we notice, of course we listen to y'all, and we know that these reports are pretty annoying. So I figured one way to help that was to, instead of writing everything, you just tell us the things. But yeah, so just a heads up there. Anyway, so other than that, that's pretty much it for the sort of the PA explanation. So right now then, what we're gonna do, or I'm gonna do real quick, let me pull it up, is we're gonna sort of walk through how the hang on, let me go track it down real quick. Yeah, that'll work. So
topological sorting will work.
Yeah. Okay. So we're going to work through an example of topological sort, because it was requested at the very beginning. At least basically, I'm pretty sure it's what you said.
Yeah.
Anyway, let me close down everything real quick. Cool. So assuming then you have this graph, okay, so you're going to want to perform a so like this assumes then you have build graph, right, and like that's already been run, but this is before you compute the in degree. So as you notice in the main, compute in degree was called before before topological sort was.
That's very important.
Yeah, because unlike, what was that one? Unlike the binary search tree where you like calculate search cost as you inserted things, that's gonna be delineated to a separate function this time. So you won't really know what the in degree of a given vertex is until you run the function. So in regards to the compute in degree, so as was hopefully discussed in class, in degree at its base level is simply
how many arrows are pointing into the node.
Yep. Yeah. So how many arrows are pointing into the node?
Yeah.
So I'm just gonna So this is simply the number of arrows pointing to the node. Okay. So makes it pretty easy. Now, in the code, of course, feel more interesting. So what you instead want to do, and I'll go through that in this example, is you would, or through that unordered map or through the hash table that you have, you would go visit the different vertices and increment their in degrees based on the adjacency list that you're at right now. Okay.
Topological sort always has to be with the directed graph.
Yeah. Yes. Yeah. Topological sort's only used with digraphs, because otherwise you wouldn't know where to go.
Yeah. Otherwise, in degree wouldn't really exist.
Yeah. It's okay. So, for example, so if you started at 1, then you would go visit 2 and you say, okay, you now have an end degree of 1. So assuming all of them are starting at 0, right? You start at 1, or you start looking at 1. I'm just going to go in order. Obviously, in the unordered map, or in the unordered map, you kind of just need to go through it in some way. Thankfully, for our purposes, you can assume that the vertices are in order from 1 through whatever. So, yeah. But anyway, so you then say increment 4, increment 5. You visit 2. So once you're done, so you've now exhausted 1's adjacency list. So you now move to 2. 2 has 3 and 4. So 3 would go up to 1, and 4 would go up to 2. And then visit 3, which has 4. So this would go up to 3. Okay. Oh yeah, right. So, sorry, yeah. 2 has 7. Yeah, sorry, forgot about that. 2 has 7. And then 4 has 7 and 6. So this would go to 2, and this will go to 1. 7 has 6. Or yeah, 6 has 5, I guess. Yeah, that'd be what 6 has 5, and then 7 has 6. And then of course 1 is implied to be 0 because there's nothing into it. So in that manner, so you sort of go through so that would be the equivalent to that doubly nested for loop that was in the pseudocode, where you start at your starting vertex and you go around in order. So you start at 1, then you go to 2, 3, 4, 5, 6, 7, and you figure out, okay, like, does this node have anything pointing out of it? If so, go visit that node and increment its end degree. Okay. The key is to do this within your data structure. So, this can be thought of then as saying something like node underscore set bracket 2, for example, dot end degree plus plus. Okay, I'm shortening things here for space, but this would be the basic idea. So you'd want to actually go off and reference your thing within the graph itself, or within the node, within the hash map rather, or hash set, whatever.
Hash set.
Yeah.
Or, hash map.
Hash map.
Hash set.
I'm getting two things confused.
Hash set is something in Java.
Yeah. There's a lot of interesting things in Java.
Yeah. Quite useful.
Mm-hmm. So once we get this, so after we get all of our end degrees, then we can actually run topological sort. So I'm gonna have the pseudocode pulled up on the side here for my own purposes. Oh geez. But give me 1 second here.
I could go through it if you want. I kind of know how it works.
Oh, hey, that's nice. I was about to say,
Nice.
hopefully when I move it on
Since
my screen.
Since you're just sharing that part of the screen, it works just fine.
All right. Yeah. So per that, there's an initial for loop, right, inside of the topological sort that figures out or just NQs anything that's at 0 in degree. So there's only one vertex that has 0 in degree. So this will be our starting point for topological sort. Okay. So from here, so what I'm going to do for purposes of just directly translating the pseudocode, I'm going to be noting the top num value in a different color as we go. So initially the counter is set to 0. So whenever you do this, 1 would have a top num of 1 because it's plus plus counter. So it would be 1. So once you do that, then you figure out, okay, for all the vertices that are adjacent to this vertex 1, you subtract off their end degree, or you subtract their end degree by 1. So in this case, right, so you first visit 2 per the ordering. So you visit 2 first. You decrement it to 0. Okay. Once it's 0, so there's a little if statement inside there that sees if it is equal to 0.
push it to the queue.
If it is, then you push it onto the queue. So I guess off to the side here. So before everything, so before your while loop runs, you'll just have vertex 1, or you can think of just having 1 in there. It would obviously be a vertex object, not the literal number 1, but for demonstration purposes, yeah. So then as you're running then, so you dequeue this and then it's empty. So once things get to 0, like 2 does, then you go ahead and enqueue them into your queue, okay? So then we go to visit 4. This decrements to 2. This is not 0, so keep going. 1 goes to 5, which decrements to 1, but it's not 0, so we skip it. So right now then 2 is the only thing in our queue. So the next iteration then is like this, okay? So right now then we have sort of dealt with 1. So 1's now done, okay? So moving on. So 2 then has a top num value of 2 because it just increments by 1. Then we consider all of 2's adjacent things. So 2 to 3. So the 3's integrity being 1 drops to 0. So we would go ahead and enqueue the 3. 4 being 2 in degree would drop to 1. We wouldn't enqueue it because it's not 0 yet. Lastly, you then have 7, which would drop to 1, right?
Not 0.
So we only have 3 in our queue. So that's the next thing pop off. So if we sort of take all this out, so that means then that the 3's top num will be 3. I know that it's in order right now. It'll get it eventually in terms of the top nums. Anyway, so this ends up having a top num value of 3. Actually, I'll just drop that over here. So 3, the only thing in 3's adjacency list is 4. So you go to 4. And this, of course, drops to 0, which means that you enqueue 4. Okay. And then since that's the only place to go, we're going to go and go there. So this thing's top num value would be 4. Then we go to what 4 is connected to. So 4, of course, is connected to 6 and 7. So we go to 6 first. the 2 gets dropped to 1, not 0, so we move on. Goes to 7. 7 then drops to 0, which means that we then enqueue 7. I know I'm not stating the dequeues, they're just happening as I visit the nodes. Anyway, so then this thing gets taken out. So the top num of 7 ends up being 5. All right, so that's where it sort of differs from standard order. And then from here, 7 only has one thing to visit, that being 6. So it goes over here. This drops to 0. And then therefore we end up enqueuing 6 up here. Take this out. So the top num value of 6 ends up being 6, funnily enough. And then the only thing in 6's adjacency list is 5. So go visit 5. This drops to 0. Yeah, the 1 drops to 0. And then enqueue it 5. Take this out. So this thing's top num is now 7. And 5 doesn't have anything in its adjacency list. So we are now done. And then we then have this check against the number of vertices. So we are basically to assert then that we didn't have a cycle. We say, okay, how many vertices do we visit? And how many vertices do we expect to visit? So we visited 7 vertices. We expected to visit 7 vertices. So we're good. There's no cycle. And the order then is printed out based on the top num values. So in order, so 1, 2, 3, 4, 5, 6, 7. Top num, so that equivalents to what Thomas put there. So 1, 2, 3, 4, 7, 6, 5. Okay.
The way to check if your thing is correct is you look at every edge, and if there is an edge from, like, let's say 1 to 5, I'm looking at this edge right here, then 1 is before 5 in the order. And so, like, if 1 is pointing to 4, 1 should be somewhere before 4. When do you DQ?
You DQ every single time you loop.
Yeah. So your like big while loop is while your queue is not empty.
Yeah. Yeah. So sort of implicitly, what I was doing whenever I like started considering stuff at different nodes adjacency, at different vertices adjacency lists, I was implicitly dequeuing that node from our queue. I just didn't write that. I just didn't state it. Yeah. So does that at least sort of make sense? What's the figuring? Q. But yeah. So hopefully then that can help. This time around, the pseudocode's fairly detailed. It's like you don't have to add too much to get it to work. You do have to add some things though. But yeah, that's in respect to the homework.
What?
No, the homework. That's why. All right. So for the homework, right? So in this case, we actually have two different files. One of them is the homework itself. So that being this. The other one is another document which Alex has prepared. It's basically his notes about the homework. So sort of answering very common questions and clarifying what you need to do. Okay.
Where is this?
This is
the document.
No, it's on campus. This is his overleaf template, his overleaf stuff. So in general then, right, so all of your screenshots should be easy to read. We should not have like very minuscule screenshots. If that's the case, then like please like zoom them in for us, because we can only zoom in our computer so much. Yeah, so many solutions require you to draw graphs and tables. So you can use pencil, paper, bed of images. You can use other software as you see fit, as long as it's legible. So all you submit is a PDF. And then one common thing then is the idea that you should that like whenever you're figuring out the big O bound, you need to justify it with more than just this is a number of loops, therefore this is the big O. Because as we saw in the exam 1 test review sheet, right, that had a lot of different loops which were not O of n or O of n squared. In fact, there's one case where there are 2 loops, but the runtime was O of n. Okay, so more text does not equal better explanation. You need to show how the problem changes with input size. So that's not based on loops. Shouldn't be. So he has some various notes about the different questions, along with links to different files, which you might find useful. Most of these just link back to different slide sets that you already know about. This is just he just put the same information on Google Drive. So all these slide sets here are available already. This is just a handier way you can go about it if you want to. But anyway, so the homework itself has a total of, I believe, 8 or 9, 8 questions. So it's sort of going through all the different things that we've learned since homework 2. So this first question then is simply giving you a scenario and asking you what data structure to use. It says, okay, so you have an airport and it has some timestamps that it's logging, and you want to insert an event with a given timestamp and then extract the event with the smallest timestamp. Okay, now what I will say with this data structure, or this question specifically, is that we always get questions about it because people don't read the question super well. So what I would say here, to figure out what data structure we mean, look at what it does. Look at what it does. The only other thing I will add is that whenever you are describing the data structure and providing its big O for the insert and extract min, these need to be the most efficient possible. Okay, so by most efficient, I mean, yeah, that's about all I can say. Because again, this is a very easy question to accidentally give the answer away to. So it's better for me to just say nothing than to keep talking. So we're gonna move on. Yeah, just know though that I promise you have seen this before. You just have to take what these two things are. Okay. Anyway, so then just give their big O's for the insertion and extract min to assert that this is the most efficient thing that you could do. Okay. Second thing is a more sort of manual task. That being, we want you to go through a hash table and use this hash function we provide for you to figure out how to hash the keys we give here. Okay. So you assume, so that's sort of tabulated down here. So we have different insert calls, and you need to give us what indices they're at, as well as what indices you get first. So you will end up with collisions, right? So you'll have to deal with those using the double hashing method. So you have a secondary hash function here. And as we say here, so we want you to provide the final state of the table. So give us what your final result is, and then also tell us what different indices you like, or what different indices you ended up like skipping whenever you were hashing, right? And for context, I don't know if he said it over here. He might have said it. Hang on. So he might have said it. I know that
Double hashing.
Yeah, this thing. Okay, this specific function formula is what you need to use. Okay, double hashing in of itself is very easy, but you need to figure it in, because I know that this is one of the things that most people are confused about because they don't know what I is. So the way to read this, so first of all, your table size. So what we mean by table size is quite literally how many available spaces do you have? Okay, so that's not mod 11 or mod 7. That's the overall mod that you need to do whenever you end up using these other hash functions. So in general, then h1 is going to be the first hash function we gave you. So that's that mod 11 one. So that's one you use by default. But if you run into a collision, that's where you then need to use the secondary hash function, that being the one that's mod 7. Okay, now this I thing, all this is you start out at 0, and then you increment it by 1 if you end up running into collisions. Okay, collisions being simply there's something already there. Okay, so for example, you could say have 44 mapped to the same thing as 12, say index 2 or something. Let's say 44 and 12 theoretically map to 2. They don't actually, but whatever. So if both 44 and, what did I say, 12? I think it's 12. Yes, 12. If they both map to the same value being 2 or the same index within this hash function, that's a problem. So when that's a problem, you would then take whatever you just hashed being 44 and you recalculate an index for it based on incrementing this I from 0 to 1. So this then makes it such that you compute the second hash function value. So this would be, say, another just index, say, 5 or something. And then what this one ended up being then, or you end up computing this, you end up computing 2 plus 5 times I, where I is 0, 1, 2, 3, 4, whatever. And you do this until you find a valid index where there's nothing there. Okay, and then you tell us what indices you had to visit in order to get to your final result. Okay, so in other words, we want those intermediate steps when you're sort of figuring out where things are. Okay, so again, we'll sort of probably end up doing this more next time, but yeah. So then third question is in regards to a complete graph, in regards to graphs. So actually, here, let's just make this tiny. So specifically, so we have 6 vertices here, and this is a complete graph because every single vertex is connected to every other vertex. That's why you get this very symmetric shape, right? And the question then, we then ask questions about how depth first search explores vertices. So we assume that DFS starts at vertex 4. So you then figure that the adjacency lists are in ascending order by numeric label. So in case you are too tired, that's okay. What all this means is that, so 4 is connected to every other thing, right? So 4 is connected to 3, 2, 1, 4, 3, 2, 1, 6, 5, right? So you assume then that 4's adjacency list is not 3, it's, sorry, 1, 2, 3, 5, 6. That's a horrible 3, but I'm gonna ignore it. So this is then its adjacency list. So this should infer a certain ordering of DFS. Okay. So yeah, this should tell you what edges you end up traveling across to get your DFS traversal. Okay. Not that I'm going to do it, of course, but Yeah. So we ask you, okay, so what's the running time of DFS on a complete graph with n vertices? Okay, so sort of thinking of, because we give a certain, or like give a certain runtime in the slides, but this is like, you need to translate it to this, right? So it's a complete graph instead of a sparse graph. There's 2 different base runtimes, or 2 different, the same theoretical runtime, but different overall, if that makes sense.
The fact that it's dense, like the number of edges as like some function of the number of nodes. Yep. That's the way to think of it.
Yeah. So then there's a question, which is what Anjali is asking ultimately about back edges, forward edges, cross edges, exploratory edges. So with that, we'll deal with that here in a second, because that takes some doing. Yeah. 4 then is just asking you, okay, so a priority queue, unsorted NP queue is planned based on unsorted array. What is the running time of the operation which retrieves the minimum value? Justify that, and so you have to justify this with algorithmic reasoning. So what that means is, don't just give us big O and just say, well, it's because that's how I implemented it. That's not an answer. So you need to be able to basically describe what this would look like, right? So an unsorted array, so you'll describe, okay, like why is removing the minimum, or why is like finding the minimum that whatever big O it ends up being. Okay, so you'd have to reason about it in general. So not in terms of, so implementation can help you figure out what the general justification is, but yeah. So in a similar manner, we ask you about Dijkstra's algorithms. That's a graph algorithm that we've hopefully maybe gone over, not yet, maybe, it's okay. It's not too hard. But we tell you it's implemented based on unsorted minimum priority queue. So therefore, what is the running time of this algorithm? So the sort of the what's called like the different priority queue implementations ultimately do impact how fast Dijkstra's runs. So yeah, as for reasons that if they haven't been explained already, or hopefully be explained soon. So we have the shortest path. So this is, in my opinion, this is one of the more fun ones, even though it does take a while. So your goal is to find the shortest path from the vertex D to all other points in the graph. So we want you to essentially run Dijkstra's algorithm on this. And as we say here in part A, we want you to give us the minimum priority queue at each iteration of the algorithm. So all that means is that you just keep track of the number of things, or like how things are set up in there. There's an example somewhere in the slides where she does this, where she has minimum priority queue. We then want you to draw the shortest path tree that you get whenever you run this algorithm. So you'll get some tree out with D as the starting point, D as the root. We want you to draw that. Okay. And then lastly, we just ask you, okay, what's the running time of Dijkstra's under the assumptions given? Okay. So we don't ask you for justification. We just ask you what's the runtime. So big O will suffice. So next one then is similar, but not the same. So we want you to find the shortest path again from a different graph from a vertex to all their vertices. And the thing to note, I think he maybe mentions it over here. No, he doesn't. Yes, there are different graph algorithms that can solve this. But notice we assert here the most efficiently.
Yes.
This is the key. So given all the graph algorithms we've gone over, or you will go over, figure out which one is the most efficient at going through this to give you, or going through what is effectively a directed, not unweighted graph, right? So you figure out that, and then you obviously need to do it, right? Because you need to draw the shortest path tree that you get whenever you end up running whatever it is. Okay, so as he says here in his notes, he says there are multiple algorithms that can solve it. So efficiently is asymptotically efficient. So if two things have the same runtime, then you use either one. But things must be efficient. So we then have this fairly simple graph, and what you want you to, this proves the point about Dijkstra's algorithm. So we want you to, again, apply it to find the shortest path from A to all the vertices. And once again, illustrate the minimum priority queue. Then we ask two different questions. So we ask you, okay, does the algorithm return the correct output for your graph? So the correct output being the idea that you did find the shortest path from A to every other vertex. So there's no other possible shorter path, right? So yeah, that's what I'm going to leave it at. And then this next question asks, does Dijkstra's theorem guarantee correctness for this graph? Explain. So as he explains over here, correctness means will provide a correct output. So as there's a theorem on one of the slides in the graphs set of slides. This gives a theorem. So as it says here, certain specifications have to be met before correctness can be guaranteed. So that's what your figuring is. Okay, so you have to explain your answer, yes or no to this. Yeah. Last one then is something we definitely haven't gone over. I don't think it's minimum spanning trees. So with this, there's two different ones that are used to generate minimum spanning trees. There's prims and there's Kruskal's. They use different methods to generate the minimum spanning tree. You should end up with the same answer regardless of what algorithm, or like across both algorithms. And then the lane. So our context for this question is you have a bunch of islands that are connected via bridges, and all the bridges, like the different bridge lengths, are given here. So for example, island 1 is connected to island 2 through a 240 length bridge. Island 1 is connected to island 8 through a 120 length bridge, etc. So your goal then is to figure out the minimal distance to connect all of the islands by one bridge. So you're essentially doing a graph traverse. You're essentially figuring out the minimum distance to get to all the different islands from a starting point being 1. Well, actually, no, wouldn't be 1 necessarily, but it's based on how the algorithm would operate. So pro tip, it probably has something to do with minimizing. I can tell you though that these two do work differently. I believe Kruskal's, from what I recall, Kruskal's does like a global minimum, Prims does like a local minimum, something like that.
Still get the same.
Like you end up with the same answer, but Prims, I believe, I'll have to go double check, but one of the two is where you're developing or has you develop a forest where you sort of go off on different tangents where you say, okay, like this node's connected to this node, and you might say, oh, like there's this other thing, I'm pretty sure it's crystals, is where you like essentially do like subtrees, and then eventually you end up connecting all of them in some way, such that you end up with some like cohesive thing. Whereas with prims, you have one set starting point, and then you sort of build out your tree from there. So you'd have some sort of set starting point, and then you sort of branch off of that. So instead of having this like essentially generating separate like collections and then combining them in the end, prims has you just has everything be connected initially. So you end up with the same answer regardless. Same answer being the total length of all the bridges that you visit. But two different ways to do it. Cool. Okay. So any other than this one, which we're going to cover here in a second, y'all have any questions about, anything you want us to clarify right now in terms of the homework? Or does it just kind of seem too over your head, and like it's 8 a.m. in the morning, you don't want to deal with it? Yeah. Again, so a lot of this is graph traversal, right? Or questions about graphs, and sort of start out with sort of easier questions about other things, and then there's just a bunch of graphs, and then you finish with minimum spanning trees. So this is a lot of sort of graph knowledge that's being thrown at you. But yeah, so I guess one thing I will note from this question, so when we say shortest path, since there's no weights to each of these, right, you can think of, say, the fact that 3 has an arrow to 1 means that the shortest path from 3 to 1 is just going to 1 from 3.
Length of 1.
Right, so yeah, so the shortest path then from 3 to 1 would be just length of 1, because it's just this, right? So that's sort of the minor clarification that might help you. I don't know. But anyway, okay. For okay, I'll have to go look it up, because I'm not entirely sure. Well, this I would prefer to have a like an assistant and some sort of helper thing, because oh gosh, I do not want to end up downloading these things. And of course now it's lagging. Thank you. Okay. I'm trying to remember too which one it is, because there's a lot of different ones. There's a lot of different things.
the one you downloaded.
Is it?
Yeah.
Oof. Thank you for telling me.
Thanks, Anjali.
Yep.
MVP.
You can tell that I know which. You can tell I know which slide set I'm in. It's more so just that there's so many of them, because there's the PowerPoints, but there's also the PDFs. Because like the PDFs were clearly made at one point, and the PowerPoints are like a completely separate thing. So yeah, and then you have the PowerPoint presentations, and like it's just it is a mess.
Yeah, it's not currently sharing right now.
It is a mess. Oh, oops.
There we go. DFS.
Yep. Okay. Yeah, so it's sort of thing I was talking about. So you have a tree, which is starting at one point. You have a forest, which is multiple things. That's how generally they work. Hang on. No. Okay. Give me 1 second. let me search around for a little bit. See if I can find it. Because I know that there is somewhere. I know there's a set of something somewhere. Just need to find it. This might take a while though. Give me a second. It's okay. I'll find it eventually.
Well, sorry, it's in digraphs. PowerPoint.
Is it? Okay, yeah. I just downloaded it. Yeah, here it is. Yes, I just downloaded it. Been like, oh yeah, here it is.
You're good on Golly.
Yeah. So
Wahoo.
anyway, yeah. So you have then, yes, this is a different thing then. So you have DFS. So you have 4 different types of edges: discovery, back, forward, cross. So as the homework states, right, so that's what we need to figure out pretty much for this. So I think the only difference is that they like discovery is replaced by exploratory in the homework, but it's the same. So different word, same meaning. So yeah. So discovery. So there's the 4 different types. Then they are all used in this, but they can be interesting. So I'm trying to remember if there's any actual example in here or if it's just kind of random. I'm pretty sure there's no actual example. It's just kind of stating that this is what it is. Yeah, that's what I thought. Yeah, that's okay.
That's the only example you get.
Yep. Oof. Yes, I'm pretty sure this is, yeah. I'm pretty sure I remember this way back whenever I was taking this class. Yeah, this was the one that's like, yep, there's really only one example in slides anyway. Probably find more elsewhere, but anyway. So the idea then, so you have this. So first of all, discovery edges are the easiest thing to explain. So discovery edges are things that you visit as you're doing depth first search. Okay. So sort of from this like explanation, you can figure out what the adjacency list was to generate this. Now I can tell you, so actually, yeah, because it's easier if I just give it. So in this case, A was connected to C, then B, okay, and then
D.
Then D. Yep. So yes, I'm gonna real quick. I'm actually gonna do this in a different color. Yeah, so I'm gonna go and just draw out what the adjacency lists are because that will help with regards to figuring out this the way this works. So again, so A is initially connected to C, then B, then D, and then I believe, yeah, B is just connected to D, and that's it. I'm under pressure.
Don't mess up, Isaiah.
Okay, I think it's E then D.
Yeah.
Right? Yeah. And then D is connected to just E. And then E is connected back to A. Okay, now I can explain how I figured this out later. It has to do with tracing exploratory edges and then figuring out which way it went first. Because I can tell that, for example, B is not first in the adjacency list, because otherwise it would have gone to B, then to D in terms of the red stuff, but it didn't. So that means that the only other choice then is C. C must have been first. And then because this edge right here is not red, that implies that this traveling to D did not happen on the first iteration of DFS. So that's how I was able to figure out the ordering adjacency list wise. Anyway, so discovery edges are edges you'd visit during normal depth first search. Okay, so in this case, we start at A, and we do normal depth first search to figure out the different edges. So if we just follow the adjacency list, right? So you go from A to C, then from C, you go to E first. E then connects back to A. So you'd go ahead and backtrack to back to C to figure out, hey, like, are there any other edges you can go on? Yes, there's one other one. There's D. So C can go to D. So that's an exploratory edge. D is only connected to E, so this doesn't count. Backtracks to A, and then A can then go to B. B goes to D, which has already been visited, so we're fine. So the blue arrows then represent the discovery edges. So those are the edges where you're finding new nodes. Okay, now you then have the back edges. So what the back edges is, that's the edge or the edges that connect back to the starting point, basically.
Or back to a previous.
Back to a previous state. So so by way of example, right, there could also be, say, an arrow from E to C, right? And this would also count as a back edge because we have already visited C, but we're visiting it again from a different node. Okay, so
but
that's
it's not. It's more like it's in the current path.
Yeah. Yes.
Back along, because you can previously visit the nodes, and it won't be a back edge.
Right. Yeah. Yes, it's sort of like in your current path. Okay. So in this case, there's only one back edge that's given, that being the edge from E all the way back to A. And the reasoning being, as I said before, so your initial traversal to go to A to C to E, and end up going back around to A, and then you back off. So this sort of back edge where you end up at your starting point forces you to begin to backtrack to DFS. Okay. Your forward edges then are the yellow ones. So that's this dot dash. And with these, the idea with the forward edge is that it's an edge that you could have gone, I'm trying to think.
Yeah. It's like depending on the order of the adjacency list, you could have visited that one first. It's like the D has already been visited, but it's not like behind A.
Yeah. So forward edges are the idea that you can visit it. You could have visited it earlier, but you didn't because of adjacency list order. So that's different than a cross edge. I know it's fine. So there's only really one forward edge here, but you could also figure that what's called that, like something like
from A to E.
Yeah. So if, say, we had an additional thing where A was connected all the way to E, then this would also be a forward edge because we visited E by going from C through E, by going through C. So this edge would not be used, but we would be noted as a forward edge because we could have gone to E first. Okay, so that's just based on ordering, right? Then these cross edges are the gray things, right? So that's these two. So one here, one here. With cross edges, the idea is that you've already visited this node before, like whatever edge it is, but you could have visited it like at the same time.
That's my guess at the same time, because
Yeah, you can tell we prepare a lot for this. Sorry, didn't have coffee this morning. It's okay. Let me think. You want to just look it up?
DFS
Yeah, that's
discovery edges that don't share ancestors.
Yeah, it's like so forward edges, or forward edges, the idea being you could go down them if you had a different ordering. With cross edges, the idea is instead it's like it's edges that are in between nodes that you visited, if that makes sense. So it's not forward edges because you wouldn't have gone down them. It's not back edges because you haven't backtracked to some other point. This is where so just big brain it. 1 second. So shit, yeah. Yeah. So that's the okay. Yeah. So from that, from the Geeks for Geeks link, right? Yeah. Which ultimately, I mean, that's really the main source of information in this course, anyway. So, and Dolly's right. So it's based on the idea that both D and B don't have, or both D and B have, well, they do have A as their as their base. So A connects to D and B, but per DFS, we went through C and then to D. So both D and B do not have the same base. So D would only know about C, and A would only know about, and B would only know about A. So therefore, this edge between D and B is a cross edge because it's connecting two different things with two different initial nodes. Okay. So again, these are all edges, right? First of all, these are all edges within the graph per the adjacency list. But the order in which they're visited in DFS matters. So in terms of how I was able to figure out the adjacency lists, right? So again, it's based on sort of figuring out these discovery edges. So noticing that, hey, this route's traveled, and then this, right? And then from there, then you can figure out, okay, like the different edges based on, or where the edges fall based on the adjacency list format. Yes, they're all edges in the graph. Yes, yeah. They're all correct. They're all legitimate edges. First a DFS and go off. Yes. Yeah. So you do a DFS to get your discovery edges, and then you figure out the rest from there. Yeah. Pretty much. So then, so your back edges then are essentially going back tracing back into your primary path. So your back edge then is such that your edge, you're going back to some ancestor node, but it's not part of the tree. And then your forward edge then is where you're basically just where you can't go there. Like you wouldn't go there for the ordering, but you might have gone there.
It's time, by the way.
Yeah. Okay. All right. So with that, we are about out of time on things. I'm going to